Hello and welcome back to Homework Help for Math 2. This time we're going to be looking at Unit 8, Circles, Angles, and Shapes, Lesson 7, Footprints in the Sand. Starting with the Ready section, question number 1 says, plot each pair of points on the coordinate grid, then find the length of the line segment that connects each pair of points. All right. So we've got our points here. I think I'll plot the points maybe in red. So we'll use that for the points. So I'll go ahead and just plot all 3 points and then connect them and then get the lengths. So our first point here is -3, 5. So that means starting at the origin, we go to the left 3 and we go up 5, and that is right there. So I'll go ahead and label that. This point is -3, 5. All right, our next point is -3, 7. So again, from the origin, we go to the left 3, and then we go down 7, and that puts us right there. And I'll label this as -3, -7. Our next point is 5, -7. So from the origin, I go to the right 5 and I go down 7, and that is right there. And that point is 5, -7. -3, -7 we already plotted. -3, 5 we already plotted. And 5, -7 we already plotted. So those are our 3 points. So plot each pair, find the length. So our length, so our first length is right there. So it is how long, or what is the distance from -3, 5 going straight down to -3, -7. Well, notice that for this length, it's a vertical line. And all I need to do here is actually just count the boxes from my top point to my point in the bottom left. So I'm going to start at 5, and I'm going to count down. Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Also, notice that if we take the absolute value of the difference of my y coordinates, so the absolute value of 5 minus -7, that's the absolute value of 12, which of course is 12. And if you do it in the other order, if you do -7 minus 5, you get the absolute value of -12, which is still 12. So no matter how you do this, you get 12. And so the length of the line segment that we just drew is, actually, let me get rid of all that extra stuff here for a second. That's going to take too long. Let's just erase all that and erase the green. And our length here is 12. Now, if I want the length from 5, -7, which is in the bottom right, to -3, -7, which is in the bottom left, we're talking about this length right here. And notice that that is a horizontal line. It's just going left and right. And so again, I can just count the boxes. So here, if I want this length, we'll count 1, 2, 3, 4, 5, 6, 7, 8. Notice also that this is the absolute value of -3 minus 5. So the absolute value of -8 is 8. It's a straight line. No, it's actually just 8, sorry. So just 8. So anyway, our length here is 8. Can erase all that and erase the counting. All right, so the last thing that we need to do in this problem is find the length that connects, the length of the line segment that connects -3, 5 with 5, -7. So it's going from here down to there, just like that. Now, to find the length of this line segment, It's a little bit more complicated than the first two, and the reason is because it's not a horizontal or vertical line. It's kind of slanted, and so we can't really count the boxes here because it's not it's not a horizontal or vertical line. However, what we do have in this picture, so the first two lines that I drew, they are perpendicular. One was vertical, one was horizontal, which means they form a right angle. So there's a right angle in the bottom left there. We already figured out that my vertical length here was 12, and we also already figured out that my horizontal length was 8. That's an 8. Okay. So what we have here is we have a right triangle where we know two of our sides, and we need our third side. So this is a classic example of where we want to use the Pythagorean theorem. The Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. A squared plus b squared equals c squared. In this equation, c must be your hypotenuse, and that just happens to be the thing that we're looking for, so we'll leave c in there. But a and b are our two legs. It doesn't matter which one's which, so we'll just say 12 squared plus 8 squared is the thing that we're looking for, c squared. I'm going to flip this equation around so that c is on the left. So c squared equals. You could plug this whole thing in as it is. I'll just do it piece by piece. 12 squared is 144. 8 squared is 64. 64. So c squared is the sum of 144 and 64. That's 208. And we'll take the square root of both. Oh, that's right. That's still a thicker line. Let's try it again. So we'll take the square root of both sides. And that gives me c equals. Because we are looking for a side length, we do not need our plus minus because we know that c cannot be negative, right? So because we know for a fact that c cannot be negative, this is a situation where we do not need to include the plus minus when we take the square root of both sides. That is only when there is any kind of ambiguity about whether the thing that got squared is negative or not. And in this case, c is clearly positive, so we do not need the plus minus. So c is the square root of 208. I'll write it out, 208. Now, in order to finish out this problem, all we really need to do now is just potentially simplify the square root. In order to simplify the square root, we need to determine what is the largest square number, okay? So a square number that goes in evenly into 208, and then some other number, okay? The other number doesn't really matter what it is as long as it's an integer or a whole number. But the first factor here, I want to figure out what is the largest square number. So if you're not sure how to do this, one way is just trial and error on the calculator. So let me go to the calculator here. So let's try. So 208. Now, it turns out that 1 is a square number, but that doesn't really get you anywhere. So you can safely skip 1, even though 1 is technically a square number. The next square number after 1 is 4. And the reason why 4 is a square number is because 2 squared is 4. So the result is 4. So therefore 4 is a square number. So 4 does go in evenly into 208. So as of right now, our largest square number is 4. All right? But let's see if there's a number larger than that. So the next square number after 4 is 9, and 9 does not work. So you get a decimal that tells you it doesn't work. So 208 is not divisible by 9. The next square number after 9 is 16, because 4 squared is 16. Now it turns out that 16 does go in evenly into 208, and not only does it go in evenly, but the other factor, in this case 13, is prime. Whenever that happens, whenever you get something like this, you can safely stop, right? You don't need to check the others, right? The next one, 208, 25. This I know this is not going to work, and it doesn't. 36 is not going to work. 49 is not going to work. 64 is not going to work. So once you get a prime number like 13 in this case, you can essentially stop there. And so what we want to do is we want to rewrite 208 as 16 times 13. So I'm going to do that right now. So 208 is 16 times 13. And specifically, 16 is the largest square number that goes in evenly into 208. I can split this up as two smaller square roots. And so the square root of 16 is 4, and then the root 13 cannot be simplified, and so that is our length for, that is our third length. So 4 root 13. And I didn't get a decimal approximation here, but maybe I'll just do that real quick. So 4 square root of 13 is approximately 14.42. Also, to check our answer, notice that if I do the square root of 208, our original answer, we actually get the same decimal. So this is actually a really great way to check and make sure that these two quantities need to be the same, because they are the same number. It's just the first one, 4 root 13, is simplified. So it's always a good idea to check if you're ever not sure whenever you're simplifying square roots, do you get the same decimal as your original thing that you're trying to simplify? So this is approximately 14.42. So this is approximately 14.42. If you didn't write the approximation, that's fine, but it is just good to check that it's also the longest side, because the hypotenuse of a right triangle is always the longest side. And in this case, you have 12, you have 8, and you have 14.42. So it is, in fact, the longest side. And I think that's all we have to do for question 1. Question 3 says, what made the third length in problems 1 and 2 more difficult than the others? All right, well, we just sort of looked at what was involved, just as a refresher. In question 1, we got the 12 without too much difficulty, we got the 8 without too much difficulty, and then getting the 4 root 13 certainly took more work than the first two. It's like, why is that? What caused that to happen? So for this one, we'll type it out. So what made this more difficult? So in the original picture, the third side was slanted. Right? And so what that means is you can't count the lengths using the grid, right? So what made it more difficult is that the segment, we only did problem 1, so it's 1. So the one segment is drawn on the diagonal. So it can't be counted using the grid. All right? So we need to use the Pythagorean theorem for these problems, because you can't just count them, like I said, using the grid. However, when the segment is a vertical or horizontal line, the distance can be easily counted using the grid marks. So for the first problem that we did, because it's drawn on the diagonal, we can't use the grid to count. We have to use the Pythagorean theorem, which is not impossible, right? Certainly within the capability of anyone in this class, but it is a little bit more work. But when we're dealing with either a horizontal or vertical line, our job becomes easy because we can just count the boxes and we don't have to really do any calculations per se. Continuing on with the set section. Set section starts with a table here where they provide some volume formulas for us, which is nice of them. So we've got 4 formulas here. They're all volume. The first one is for the volume of a rectangular prism. They're telling us that the volume is the length times the width times the height. They're also telling us that the volume of a pyramid is length, width, height divided by 3. The volume of a cylinder, volume is pi r squared h. And then for a cone, the volume is pi r squared h divided by 3. Quick side note, notice that for both the prism and the cylinder, these can be generalized as the area of the base times the height. Right? So any prism or cylinder, your formula is the area of the base. So with a rectangle, that's length times width times the height. And with a cylinder, your base is a circle. So that's pi r squared times h. And then for the pyramid and the cone, our volume is again the area of the base times the height, except now it's divided by 3 with both a pyramid and a cone. So, also technically this should be a rectangular pyramid. There are other kinds of pyramids, but it's safe to assume that in this formula they're talking about a rectangular pyramid, and so that means it's a pyramid with a rectangular base. So, taking a look at question 4. Question 4 says, a marble pyramid with dimensions as shown was sculpted from a marble block. Find the volume of the pyramid. So, we don't have to make this more complicated than necessary. They gave us a formula. So when they give us a formula, let's not make this too crazy. Let's just use the formula that was given. So we have a rectangular pyramid here, and we're told that the volume is length times width times height divided by 3. It doesn't really matter what you make the length or the width or the height here. You can mix them up and you'll get the same answer because multiplication is commutative. But we'll go ahead and we'll just say that 3 is the length, 4 is the width, and it makes sense that 2 would be the height in this situation. So our length is 3. Actually, I'll write out the general formula first. So our volume is length times width times height divided by 3. Notice that the way I write my L's, that's to make sure that I don't confuse that with the number 1. So when you're using a lowercase l, just be real careful that you don't confuse that with a 1. So I kind of make it very obvious that we're not talking about a 1 here, we're talking about lowercase l. So our length is 3. Our width is 4, our height is 2, and we're dividing that all by 3. Oh, my 3's cancel, and I'm left with just 4 times 2, which is 8. Our units here are feet, and because it's volume, volume is a 3-dimensional unit of measurement, therefore it is cubic feet. Right? Volume is always measured in cubic units, whatever your units are. And that is our answer for number 4. Question 5. The pyramid shown in problem 4 was chiseled from a block of marble with the dimensions of 3 feet by 4 feet by 2 feet. So they're giving us the dimensions of the block that this pyramid came from. And maybe I'll scroll back up so we can just look at the pyramid again. So this pyramid came from a block, and it's telling us that the original block was 3 by 4 by 2. I'm actually going to try to draw it. Let's see if this works out or not. So the original block, let's see, what would this look like? So it would look something like, let's see, it would look something like, maybe like this. See if this works. Okay. Okay. Scroll up a little bit. And again, this is not strictly necessary, but I do think that it might be helpful just to sort of visualize what's happening here. Maybe something like that-ish. something like that, ish, something like that, and then down, and then that apex is sort of intersecting right there, and this just comes down and is my height. Okay, so I don't know if that helps or not. Hopefully that doesn't make things more confusing, but you can kind of see how the original block was, not a cube, but almost like a cube. And then from that rectangular prism, we chiseled away, and now we're left with the pyramid that was like inside the block. So 5a is asking us how much marble in cubic feet was chiseled away. Well, if I take my original block and I subtract the pyramid, the difference is going to be what is no longer there, right? Because the pyramid plus whatever I got rid of, that together makes the block. So if I want to know how much was chiseled away, what I can do is I can first find the volume of the block. How much marble did I start with before I started chiseling anything away? And we're told that the dimensions were 3 by 4 by 2. And our formula for a rectangular prism is just length times width times height. This is the area of the base times the height. So if I want the volume of the block, it's simply 3 by 4 by 2. We just multiply them all together, and I get 24 cubic feet. That's the volume of the original block. If I want the volume that was chiseled away, I can take the original block, which we just found to be 24 cubic feet, and if I subtract the pyramid, which was 8 cubic feet, whatever the difference is going to be the amount that's no longer there, that got chiseled away. So 24 minus 8 is 16 cubic feet. And that represents the volume of the block that's no longer there. 5b says, what fraction of the marble block was discarded? Well, it tells me, we just found that 16 cubic feet was discarded, and that was out of a total of 24 cubic feet. So this represents the fraction that was discarded. If you type in 16 divided by 24 and hit math, enter, enter, it'll reduce the fraction for you. If you can't do that, or you don't want to do that, or whatever, you don't have access to a calculator, in order to simplify this, we want to find the GCF of 16 and 24, and the GCF of 16 and 24 is 8. So 16 divided by 8 is 2. 24 divided by 8 is 3. And so the fraction that was chiseled away was 2/3. So this pyramid only represents 1/3 of the original block, which, oh, hey, by the way, my formula for a pyramid is literally 1/3 of the prism. So it kind of makes sense, right? If 1/3 is what's left over, then 2/3 is what we no longer have. And we just sort of proved that again with 5b. Question 6. A decorator for a resort ordered a bigger pyramid similar to the pyramid in problem 4, but scaled up by a factor of 3. So we have a scale factor of 3 in this case, so every dimension is going to be multiplied by 3. Find the volume of the new sculpture. Well, there are 2 ways of doing this problem, and I'll do both just so you can see. One way to do this problem is to take our scale factor, which is 3, and obtain new dimensions, a new length, a new width, and a new height, and then find the volume of that new pyramid. So our original length was 3, so we'll call this L2. So L2 is going to be L1 times 3. And L1 was 3, So this is simply 3 times 3, which is 9. That's my new length. Likewise, my new width, so W2, is I can take my original width, multiply by 3. My original width was 4. And when I scale that up by 3, I get 12. And my new height is my old height times 3. My old height was 2. I apply a scale factor of 3 to that, and I get 6. These are all measured in feet. And so now if I want my new volume, I take my new length, which is 9, my new width, which is 12, my new height, which is 6, and I still divide by 3, because that's my formula for the volume of a pyramid. And if I do 9 times 12 times 6 divided by 3, you could simplify that if you want. Well, you have to simplify it, but you could potentially do this in your head. But if you don't feel like doing it in your head, you get 216 cubic feet, and that is, in fact, our answer. Now, that's one way to do this problem, and it's not a bad way to do it. It's really not like that much extra work to do it that way. If I had to identify which method is like quote unquote better, I think I'd probably go with the second method, the method that we're going to do right now. But if you solved this in the first method and you got 216, that's good. Hold on to that. The other way that you can do this problem is to actually, instead of dealing with a new length, a new width, and a new height, you should actually just jump right to the end and just determine your new volume. Like that's your first step. Now, in order to do this, you need to take the original volume, which we solved for in question 4, and we need to apply our scale factor. Now, a scale factor is 3. When we determined our new length, our new width, and our new height, all we had to do was multiply by 3 because length, width, and height are all one dimension. They're all essentially lengths, right? They're just in different directions, but they're all one dimension. Volume is 3 dimensions, which means if we're going to compare volumes using our scale factor, it is not sufficient to simply multiply by 3. That is not going to work. With a 3-dimensional unit of measurement, the impact of the scale factor is it's an exponential impact. And so we don't want to multiply by just 3, but we want to multiply by 3 to the 3rd power. And that 3 in the exponent is because this is a 3-dimensional unit of measurement. So the original volume was 8, and 3 cubed is 27. And if you do 8 times 27, you'll get the same exact 216 that we got using the first method. Like I said, both methods here are mathematically sound, and the first method isn't bad. It's not like that much extra work. But if you can recognize how to apply your scale factor in higher dimensions, so 2 dimensions, 3 dimensions, theoretically 4 dimensions, right? It doesn't really matter. You just have to take your scale factor and apply an exponent to it to account for the fact that you're no longer dealing in 1 dimension, but you're dealing, in this case, with 3 dimensions because we're talking about volume. Question 8. 8 says, a movie theater sells buttered popcorn in a cone and in a bucket. The cone has a diameter of 6 inches. So notice right off the bat, diameter, not the radius. That is key. All right? So you know that we're going to be dealing with circles here, and they give us the diameter, and that's great, but we want to use the radius. So as soon as you see the word diameter, sort of alarm bell should go off in your head. Just remember, the diameter is fine, but what we really want is we want the radius. So the diameter is 6, and the height of our cone is 10, as you can see in the picture right there on the left. The bucket has an 8-inch, once again, diameter. Be very careful. So it has an 8-inch diameter and a height of 8 inches, as you can see on the right. The cost of the cone of popcorn is $3.50, whereas the bucket of popcorn costs $10. Is the price of the bucket reasonable and fair? Justify your answer. All right. So in the context of this problem, we're basically going to say, all right, well, let's use the cone to sort of figure out what the fair price is, and then we're going to figure out if people are getting ripped off or not with this bucket, because it's clearly bigger, but it also costs more. So, is it better to get a bunch of cones, or is it better to get one bucket? What's the better situation here? And does this price for the bucket, are people getting ripped off here or not? So we're talking about popcorn. And I don't know about you, but if I were to get either of these things, what I would care about is I would care about the amount of popcorn inside the figure. I don't care about the surface area on the outside of the cone or the bucket. I certainly don't care about the height or any one-dimensional or two-dimensional unit measurement. I care about what's inside. That represents volume. So volume is the amount of space inside the figure. So with both of these, we want to just solve for the volume. So I don't have a lot of space here, but we should have enough. So what I want to find, let's start by finding the volume of the cone. So the volume of the cone is volume of the cone. All right. So our formula for the volume of a cone is, and I'll just rewrite it here, is the area of the base, which is pi r squared, because it's a circle, times the height of the cone. Right? That would give us, if we left it like that, that would be the volume of a cylinder that had these exact measurements. But because it's a cone, we have to divide by 3. So that's our general formula. So let's go ahead and plug it in. Pi, we want r. Notice that if we have a diameter of 6, our radius is going to be half of that, which is 3. So we want to use 3, not 6. So this is pi times 3 squared. And then the height of a cone is from the base to the vertex, which you can see here is 10. And that all gets divided by 3. So we can clean this up a little bit. One of our 3's cancels, and we're left with 3 times 10. So that's 30 pi. And we're talking about inches, and it's volume, so it's cubed. And if we plug in for pi, which I guess technically we don't have to, but if we do plug in, we get approximately 94.25 cubic inches. That is the volume of the cone. We are now going to do the same exact thing with the cylinder on the right. So again, we want to find the volume. So the volume of a cylinder is the area of the base, so pi r squared, that's how you find the area of a circle, times the height, which is the distance between the bases, which in this case, well, actually, we're just plugging in, we're just writing the general formula first. So it's pi r squared h, that's in the table at the start of this assignment. So let's go ahead and plug it in. Pi, we want our radius. So our radius is half of the diameter, which is 4. So we want to use 4 here, not 8. So we end up getting 4 squared, and then our height is 8. And we don't divide by anything in this case. So 4 squared is 16. 16 times 8 is 2 to the 7th, which is 128 pi. Don't forget the pi. And again, we're dealing with inches, and it's volume, so it's cubic. And if I want to approximate this, which might not be necessary, but it'll just take a second. So this is approximately 402.12 cubic inches. Okay. So clearly the cylinder is bigger. We probably already knew that. But what we really want to figure out is we want to figure out how does the cost factor into this, right? So with the cone, if we want for our what we essentially want is we want to figure out, all right, what is our ratio of our volume to cost or cost to volume? And it doesn't actually matter whether we do volume over cost or cost over volume, but whatever we do, we have to be consistent, and then we also have to sort of interpret that in the context of the problem. So what I'm going to do is I'm going to just kind of choose to do, I'll do this over here on the left. I'm going to choose to do volume over cost. Okay, so I'm going to do volume over cost, and because I'm doing volume over cost, I sort of want this number to be large. You know, if I'm the one buying the popcorn, well, I want a lot of popcorn for a small cost. So because I'm doing V over C, it's a better buy. It's a good buy if this is a large number. So for the cone, my volume, I'll use my exact answer. So my volume was 30 pi, and this was cubic inches. And my cost in the description was $3.50. So if I go ahead and I do this division, if I do 30 pi divided by 3.5, what I end up getting, when all said and done, I end up getting 26.93 cubic inches of popcorn per dollar. So for every dollar that I spend with the cone, I get approximately 27 cubic inches of popcorn. Okay, so that's sort of our baseline. The whole point of this question is to now do the same thing with the cylinder and compare that to my ratio for the cone. If I do the same thing with the cylinder, and if I get a number that is larger than 26.93, then the cost of the cylinder is reasonable and fair, and certainly justified. However, if I get a smaller number, it means that I'm getting less popcorn for the same amount of money per dollar. So let's go ahead and figure this out. So for the cylinder, I'm again going to do V over C, because that's what I did the first time. I'm kind of locked into that now. My exact volume was 128 pi, and this is cubic inches. And this is going to be over the cost. We're told that the bucket of popcorn costs $10. So now what I want to do is I want to take 128 times pi divided by 10, and I get approximately 40.21 cubic inches of popcorn per dollar. So for every dollar that I spend, I get 40.21 cubic inches, and I end up spending 10 of them. But per dollar, I'm getting about 40 cubic inches. So with the cone, I get about 27 cubic inches per every dollar that I spend. And with the cylinder, I get approximately 40 cubic inches for every dollar that I spend. And so for the question, is the price of the bucket reasonable and fair? My answer here is yes. Yes, it is. And I'm not really sure what else we would need to say here. Really, all we need to say is that 40.21 is, we'll even include our units here, inches per dollar, is greater than 26.93. cubic inches of popcorn per dollar. So I think that's a sufficient explanation. And anyone could look at our work here and sort of understand what we did here. So the cylinder is a good buy. And if you like your popcorn, it's a better use of your money. And finally, we're going to wrap things up here in the Go section. So the directions for the Go section are relatively straightforward. Find the degree measure of angle A. All right, so for question 9, we're given a right triangle, ABC. C is a right angle. And we're told that two of our legs are 15 and 10. And again, we're looking for the measure of angle A. So we're looking for the measure of this angle right here. In order to do this problem, I really don't want to do extra work, which means if I don't want to do extra work, I really don't want to have to find my third side unless I absolutely have to. So in this case, we know both of our legs. We don't know the hypotenuse. Now, we do know that with a right triangle, when you are given two sides, and if you want the third side, you can always use the Pythagorean theorem to get your third side. And we could do that. You could set up a squared plus b squared equals c squared, therefore 15 squared plus 10 squared equals c squared, and solve for c. But that doesn't really get you any closer to solving the problem because we want the measure of angle A. So I really don't want to get that third side if I don't have to. And in order to solve this problem, what we're going to need to know is we're going to need to know the definition of our trig ratios in a right triangle. So our trig ratios, and I'll write them down here. So the definition for sine in a right triangle is opposite over hypotenuse. That means when you find the sine of some angle, the result is going to be this ratio that is the leg that is opposite the angle you're talking about divided by your hypotenuse. The definition for cosine in a right triangle is the leg that is adjacent to your angle, again, divided by your hypotenuse. And the definition for tangent in a right triangle is the leg that is opposite your angle divided by the leg that is adjacent to your angle, or O over A. Chances are you've heard of the mnemonic of SO, CA, TOA. That's one way of remembering this. Sine, so that's SOH, CA, CAH, TOA, TOA. Just kind of a handy way of memorizing these formulas. And if you do not yet know these definitions, I would strongly encourage you to try to get them into your brain because you're going to be using them again and again and again and again and again in this class, in subsequent classes. So sine, cosine, and tangent, we would like to know those definitions. And again, these are the definitions that are specific to a right triangle. As you get into higher level math classes, you will encounter trig in other situations besides a right triangle. And in that situation, your definitions might, quote unquote, change a little bit. But because we're talking about a right triangle, these definitions are sufficient for now. So with question number 9, I think it's going to be helpful to label this triangle in terms of angle A. And in order to reduce confusion, I'm going to use lowercase letters. You won't notice it for the O, but for the A and the H, I'm going to use lowercase. So our hypotenuse is always across from the right angle. So that is my hypotenuse in this case. I don't know it. Now, because we want the measure of angle A, the leg that is opposite angle A is the 10. So I'm going to label that with O. And the leg that is adjacent to angle A is the 15, so I'll label that as A. In this situation, when you want to know the measure of an angle and you only know two sides, you want to use the trig function that connects the two values that you know. So we know 10, which is opposite. We also know 15, which is adjacent. So between sine, cosine, and tangent, the trig function that you want to use here is the one that connects both opposite and adjacent. Well, you can tell just by looking at it that that has to be tangent. So for number 9, you really want to use tangent in this situation. In order for you to use sine or cosine, you would need to know the hypotenuse, which we can get, but why bother? Why bother getting the hypotenuse if we don't need it? It's just extra work. So let's just use tangent, and we can just ignore the hypotenuse completely. So the tangent of A, of angle A, we know that that's going to be opposite over adjacent. Well, opposite is 10, and adjacent is 15. Now, we don't have to reduce our fraction, but we can. So our GCF here is 5, so this reduces to 2/3. Again, not strictly necessary, but also not a bad idea. So tangent of A is 2/3, and the thing is, I want to get A by itself. And actually, let me. I'm going to move this a little bit. I'm going to move it over here. So tangent of 2/3. No, sorry. Tangent of A is 2/3. So tangent of A is 2/3, and I want to get A by itself. And the only thing preventing A from being by itself here is the tangent function, right? We're close to getting A equals, but we have the tangent of A. Well, to get rid of tangent, we're going to use the inverse of tangent. And the inverse of tangent, it doesn't have a very imaginative name, it's just tangent inverse. Occasionally, you may see this written as arctan. So just as a FYI, tangent inverse is essentially the same thing as arctan. And if you get into some upper levels of mathematics, you may start to see that, but they're basically saying the same thing. So tangent inverse of tangent, well, they're inverses, so they cancel each other out. So I'm left with just A. Well, that's great. Now, whatever I do to one side, I have to do to the other side. So I also need the tangent inverse, or arctan, of 2/3. Now, it turns out that that's our answer, right? The tangent inverse of 2/3. That is our exact degree measurement. That's our exact measurement, regardless of whatever degrees or radians. But that is our angle measurement. Now, that's exact, but it's not very useful. So in this context, I think it's really strongly encouraged to get a decimal approximation here. So we're going to go to our calculator. All right, first things first is we have to make sure that we're in the correct mode. Now, maybe we're familiar with radians at this point, but there's almost no context in which you would be solving for a radian measure of a right triangle in this context. So we definitely want to use degrees. In order to get degrees, notice at the top of my calculator it says radians. So I want to go to mode, and I want to go down to where it says degree, and I want to go over to it, and I want to press enter. And I know that I've done this correctly if now the top of the calculator says degree. If you have an older model of a graphing calculator, you might not have up top here, it might not say all this, but you should still be able to go to mode, go to degree, press enter, and degree should be highlighted, even if it looks slightly different than this model. So I'm now in degree mode, so I can press second mode to quit. And what I want is tangent inverse. Notice that tangent inverse is in blue and it's above tangent. So if I press second tangent, that brings up tangent inverse. And I want tangent inverse of 2/3, close parentheses. I press enter. And I end up getting my degree measurement, because again, our calculator is in degree mode. I get my degree measurement of an angle that produces a tangent ratio of 2/3. And that degree measurement is 33.69. So if I go back, I can say that my final approximate answer is 33.69 0.69 degrees. And that is my final answer here. Question 10. For question 10, our directions have not changed. We want to solve for the measure of angle A, which is right there. We are again given a right triangle. We again know two sides. We are missing the third side. We could use the Pythagorean theorem to get our third side, but I don't want to. Instead, I want to make less work for myself, and I want to just figure out which trig function connects the two sides that I know relative to angle A. My hypotenuse has to be the 25. That does not change. That's across from the right angle. And because we're talking about angle A specifically, my unknown side is opposite, and the 7 is adjacent. So now the question becomes, which trig function, sine, cosine, or tangent, connects the two things that we know so that I don't have to find opposite, and I can just save myself a bunch of work? So looking at our definitions here, the trig function that connects adjacent and hypotenuse is cosine. So for question 10, our job is going to be significantly easier if we use cosine. In order to use sine or tangent, we would need to solve for opposite, and I don't feel like doing that. So the cosine of angle A, the definition for cosine in a right triangle is adjacent over hypotenuse. In this case, adjacent is 7, and my hypotenuse is 25. 25. So just like before, let's see, can I keep doing this. Let me leave enough space here. I'll write this in the middle. So we just said cosine of A is 7 over 25. All right. So I want to get A by itself. A is almost by itself, except it's kind of trapped inside the cosine function. So in order to get rid of cosine, we're going to use the inverse of cosine, which is cosine inverse, also called arc cosine sometimes. So the cosine inverse of cosine, they cancel because they're inverse operations by definition, and so I get A equals, which is what I want. I found the cosine inverse of the left, which means I also need to find the cosine inverse of the right. 7 over 25 does not reduce. Not that we need to reduce it, but we can't in this case, so we're just going to leave it as 7 over 25. That is my exact answer. Not a very useful answer, so let's get a decimal approximation here. So it's cosine 7 over 25. So we're still in degree mode, so I don't need to change it, but I just want to verify that I'm in degree mode. I do second cosine to bring up cosine inverse, and we're going to go 7 over 25, close parentheses, and I end up getting a 73.74. So this is approximately 73.74 degrees. And that is the measure of that angle. We didn't do this with 9. Maybe I'll just jump back up to 9 real quick. Oh wait, did I write my answer for 9? No, I didn't write my answer. Oh, I erased it. But our answer for 9 was about 34 degrees. And even though we're not told that this picture is drawn to scale, it kind of looks like it is. And so if you look at angle A for number 9, getting an answer of about 34 degrees kind of makes sense, just visually. And with question 10, again, we're not told that these are drawn to scale, but it kind of looks like it's drawn to scale given the 7 and the 25. And so we'd expect angle A, it's kind of like a large acute angle. It's definitely less than 90, but not by a whole lot. So getting an answer that's about 74 degrees, given the way that the picture looks, kind of makes sense if this picture is drawn to scale, which it kind of seems like it is. Question 11. Again, we want the measure of angle A. Again, we know two sides of a right triangle. The hypotenuse is always across from the right angle, so 37 is my hypotenuse. Because we're talking about angle A, that means that the 17 is opposite and the adjacent we don't know. I really don't want to solve for adjacent if I don't have to. So the question becomes, what is the trig function that connects opposite with hypotenuse? If you know your definitions, you probably already know the answer. If you don't know the answer, take a look at the left. Try to find the trig function that connects opposite with hypotenuse. And by now, I think just about everyone can recognize that we want to use sine in for number 11. If you want to use cosine or tangent, you would need to know adjacent, which means you'd have to use the Pythagorean theorem. And with these numbers, 37 and 17, that's going to be kind of a pain. So I definitely don't want to do that. So let's just use sine and keep this simple. So the sine of angle A, the definition for sine is opposite over hypotenuse. So opposite in this case is 17, and my hypotenuse is 37. So this equation says, all right, well, take your angle measurement, plug it into the sine function, and the result is going to be 17 over 37, which is about 1/2. It's just barely above 1/2. So it's 0.5 something. But anyway, I care about angle A, and so I want to get A by itself. So I want to undo sine, and in order to undo sine, we're going to apply inverse sine, or sine inverse. So the sine inverse of sine, they wash away, and we're left with just A. I have to do the same thing on the right-hand side. So sine inverse of 17 over 37, which can't be reduced. Not that we need to reduce it, but even if we wanted to, we can't. Going to go back to my calculator. We are still in degree mode, so that's great. Sine inverse of 17 over 37. Always a good idea to close the parentheses. And we end up getting 27.35. So A is approximately 27.35 degrees. And again, we're not told that this picture is drawn to scale, but it looks like it might be given the sizes of the 17 and the 37. So angle A looks kind of like a smaller angle. And so an answer of 27 degrees, assuming that this picture is drawn to scale, certainly makes sense because it's definitely going to be smaller than angle B for number 11. So for number 11, final answer, 27.35 degrees.